All right, today we're going to be looking at section 9.2, estimating a population mean. Some of the objectives are to obtain a point estimate for the population mean, state the properties of the student t-distribution, determine t-values, construct and interpret a confidence interval for a population mean, and determine the sample size needed to estimate a population mean with a specified margin of error. All right, so you have some pretty good reading and introduction that kind of goes over the details. Tells you about the variability that is introduced when you use S, the sample standard deviation, versus sigma, the population, which most of the time we won't know the population. So as you kind of read through all that, it kind of leads you to the definition of the student t-distribution. So it's just like Z, except the student t is taking into account the variability introduced by the sample standard deviation. So this time, instead of a Z value, we're looking at a t value that's equal to the sample mean minus the population mean divided by the sample standard deviation over the square root of n, which is the standard deviation for this. Student t distribution with n minus 1 degrees of freedom, where x bar is the sample mean, s is the sample standard deviation, n is your sample size, and it tells you that up there. So this is the big takeaway for student t distribution. Most of this we will, however, do with MyStatLab. So you got a little example here. I talk about Minitab or StatCrunch. StatCrunch is what I meant. Gives you some more properties about the shape of the distribution. And then here we get to the properties of the t-distribution, so this is also going to be very important. The t-distribution is different for different degrees of freedom, so different sample sizes. The t-distribution is centered at 0 and symmetric about 0, so kind of like the normal curve, the bell curve. The area under the curve is 1, so 100% or 1. The area under the curve to the right of 0 equals the area under the curve to the left of 0, which is 1/2. So you got half on the left and half on the right. For as t increases or decreases without bound, the graph approaches but never reaches 0. So that means as this graph goes further and further out, it's getting closer and closer to this x-axis, but it's never going to be 0. It looks like it does, but this little gap is probably a better picture. It just keeps going out, but it's getting smaller and smaller. Never getting to 0. The area in the tail of the t-distribution is a little greater than the area in the tails of the standard normal distribution because we're using S as an estimate of sigma, therefore introducing further variability into the t-statistic. So that's what I was kind of mentioning earlier. And then 6, as a sample size n increases, the density curve of t gets closer to the standard normal density curve. This result occurs because the sample size increases, the value of s gets closer to the value of sigma by law of large numbers. Okay, so those are the properties. And then it talks about finding z alpha or t alpha, and here are the steps to the right, and they're showing you how to find that with the degrees of freedom, which I will use a table and show you that as well. So here's the table that they're talking about. Critical Z, area under the curve, right of 10%. So this is the area on the right, 10%, approximately 1.28, which is smaller than the critical value of T with 15 degrees of freedom. So they're showing you 15 degrees of freedom. T is 1.341, where the Z would be 128. So this is because the T distribution is more spread. So they're just showing you. If I was doing 10% to the right, 15 degrees of freedom, you go down degrees of freedom, find that percentage, and then you get your answer. So how to construct and interpret a confidence interval. So here's this box. 1 minus alpha times 100%. So provided that the data come from a sample, a simple random sample, or randomized experiment, the sample is small relative to the population size. So 5% of the population size is less than, n is less than that. And the data come from the population that is normally distributed. The sample size is large enough. So if that is the case, then we can find the confidence interval The lower bound would be the sample mean minus the t statistic times the standard deviation over square root of n, and the upper bound would be that same calculation plus n minus 1 degrees of freedom is that t-score. So margin of error is defined as the t-score times the standard deviation, so s over the square root of n. And then some normality conditions and some other terms that we need to be aware of. So normality condition, most distributions are not exactly normal, so we need to verify the data appear normal enough before using the t-distribution. So option 1 says if n is less than 30, we're going to draw a probability plot. So these are some things that we might not necessarily do, but these are things you do need to be aware of. So if we're less than 30, we need to draw a normal probability plot, check normality condition, and the box plot, check for outliers. If the data appear to come from a population that is approximately normal with no outliers, then it's reasonable to use the t-distribution. So a normal probability plot is going to plot like a scatter on a plot and see how normal it is. And if you see roughly a straight line, then it's close to normal. And then a box plot will give you a 5-number summary, and then if there's no outliers, those are the things this is we're wanting you to check for. Option 2, robustness of constructing confidence intervals. An inferential method is robust if it is accurate despite minor departures from its underlying assumptions, such as the assumption of normality in the student t-distribution. So n less than 15, use the student t-distribution to construct confidence interval about the population mean. If the sample data are symmetric with no outliers, the data should not be skewed left or right. The condition may be verified with the box plot. So if n is less than or equal to 15 or between 15 and 30, you can use the distribution as long as you don't have any extreme skewness. And then if n is greater than 30, use t-distribution to construct confidence interval. This relies on central limit theorem, so it's approximately normal. The advantage of option 1, it removes subjectivity in determining whether a particular box plot is showing too much skewness. Okay, so those are some things you do want to be aware of, not awareness. And then here's an example, kind of goes over, here's that normal probability plot that was, you see how it's kind of not exactly straight, but roughly going upward in a straight line. This box plot, however, this would be the median, and then there's a whole lot more, a bigger gap between this first quartile and the median than the second quartile and the median. So this one would be like roughly skewed right. So I would say that this would not really fall into the normal model. And you can probably read through this. It says because sample size in 16 and the skewness is not extreme, the requirements of constructing a confidence interval are satisfied. So I guess it's saying it's not extreme, even though you can kind of see there's some skew to the right. There's no outliers. It don't show any really big points. And then the last thing is determining the sample size. So the sample size required to estimate the population mean with a level of confidence 1 minus alpha times 100% within a specified margin of error is given by this. So this is just taking the margin of error formula and working backwards. If you multiply by square root of n, divide by e, you get this part, and then you take these, you square both sides to get rid of that square root, and then you get this. It's doing a little algebra. So it's not really a new formula. That's something we can get from knowing the margin of error and working backwards. And then there's an example of that. All right, and then here's some steps on how to do it in the calculator, Minitab, Excel, StatCrunch, and with that, we'll jump into my math lab and start doing some problems.